Hello everyone and welcome to this presentation. First of all, I would like to thank you for this valuable opportunity to take part in this event. As you can see in the slide, our presentation takes place under the following title: Hydrothermal Synthesis, Characterization and Photocatalytic Application of Cobalt Sulfide Nanomaterials. To do this presentation or to carry out this presentation, we will adopt the following plan. First, we will start with an introduction. Then we will talk about all materials and method used to realize this work. Then we discuss our result, and finally we conclude our work. So let's begin with the introduction, especially the problematic that our work seeks to participate in its resolution, which is the global water crisis. Everyone knows that our planet is experiencing a water crisis due to a numerous reasons such as drought, irreversible usage, and pollution in all its forms. Example, the usage of pesticide, pharmaceutical products, bacteria, and organic dyes. As a consequence of these, several organizations such as the Institute of Risk Management declared that by next year, half the world's population will be living in regions subject to a water stress, and only 2.5% of the water available on the planet is drinkable. In addition, World Health Organization declared that 50% of cases of malnutrition are, are due to the consumption of non-potable water. All these realities have prompted researchers to find solutions to this problem. As a consequence of this, and as a researcher, we decide to direct a part of our research toward the participation in the treatment of wastewater. And for this, we have highlighted the following objective. Firstly, we seek to develop a new material semiconductors for removing organic dyes from wastewater, then characterize the prepared materials and study their photocatalytic performance and their recyclability as a photocatalyst. So, as we know, there is several water treatment processes, such as biological treatments, physical treatments, and advanced oxidation processes (AOP), which include ozonation, photocatalysis, and phantom hydrogen peroxide and iron ins too. Here, we choose to work with photocatalysis, which based in the use of a semiconductor materials in the presence of light. Now, which semiconductor we will use? The answer is cobalt sulfide. Why? For many reasons. Its low toxicity, low production cost, several stable phase at room temperature, key electrical and optical properties, diverse morphologies, and also its wide range of applications such as energy storage, solar cells, biosensor, catalyst for hydrogen production, and photocatalyst for removing organic dye from waste water. Now, let's talk about the second section and let's begin with the hydrothermal synthesis of our materials. Firstly, we have mixed cobalt chloride and urea in distillated water for 30 minutes. The mixture was transferred to a stainless steel autoclave, then at an oven to undergo a heat treatment at different temperature for 1 day. After the heat treatment, we recovered a greenish black precipitate which was filtered and rinsed using distillated water and ethanol. After that, we dried our product before being characterized using X-ray diffraction, FTIR analysis, cement index, and reflectance. After getting the suitable materials, we have applied them as a photocatalyst. The process was carried out in a dark room. Firstly, we mixed our product or our materials with an MB solution and we stirred them for 1 hour. After that, the reactor was exposed to UV light. After that, 4 samples of 4 milliliter were collected at specific time period to be centrifuged, analyzed by measuring their absorbance at lambda max equal 660 nanometer. So let's discuss our result. Firstly, our samples were characterized using X-ray diffraction. As you can see in the slide, the first sample is a cobalt sulfide phase COS with a hexagonal structure. The second sample is a mixture of two phases COS and CO9S8 hexagonal and cubic structures. And finally, the third sample elaborated at 220 degrees C for 1 day correspond to CO9S8 with cubic structures. So, the X-ray diffraction confirmed the formation of cobalt sulfide nanomaterials. Now let's move to Fourier transform analysis. This analysis confirmed the formation of cobalt sulfide by showing the vibration band of COS at 619 centimeter minus 1. The other vibration bands are corresponding to adsorbed water. As a result of this analysis, we can say that we have successfully obtained cobalt sulfide with high affinity to water. This result is in agreement with X-ray diffraction analysis. For the morphological and elemental study, the theme and index analysis were carried out. Firstly, the sample obtained at 180 degrees C correspond to a cobalt sulfide with nanoflower structures. The second is formed by nanoplate and the third is formed by nanohexagon. As we can see in the slide, the atomic percentage of sulfur decreases with temperature. This result is in agreement with X-ray diffraction and FTIR analysis. To determine their band gap energies, our samples were characterized using reflectance or diffuse reflectance. As we can see, all samples reflect UV radiation at the same wave. These, these spectrums have been proceeded using Kabelka-Mank function to determine the bandgap energies of each sample. As you can see from the top plot, the sample number 2 has the high bandgap energy, which about 2.89 electron volt. After that, we carried out the photocatalytic performance of each sample. For this, we have plotted their degradation rate with time in the presence and the absence of hydrogen peroxide. As we can see, our materials are able to remove MB from our prepared wastewater, and the high removal rate by adsorption for 1 hour is noted for the second sample. in the absence or in the presence of hydrogen peroxide. The same, the simple number 2 remains the best photocatalyst, which is capable or able to remove 95.09% of methylene blue from our prepared waste water. As a conclusion, the adding of hydrogen peroxide to the photocatalytic solution enhances the removal rate of methylene blue about 4% and minimizes the process time about 25 minutes. So, for the recyclability test, we carried out using the same procedure for all samples. As we can see, all samples show a high stability in the MB removal. So, and the loss efficiency was 1.77% from the cycle 1 to cycle number 6 for the sample number 1. For the sample number 2, which is the best photocatalyst, we have lost only 0.25%, or for the last photocatalyst we have lost only 0.30%. As a result of this study, our prepared photocatalysts are efficient and stable. To conclude this work, the used hydrothermal technique is an efficient method for preparing cobalt sulfide photocatalyst. The elevation of temperature influences the phase structure, morphology, and optical band gap energy of our cobalt sulfide nanomaterials. And finally, the elaborated cobalt sulfide are efficient and stable photocatalysts for MB or methylene blue removal. And thank you for your attention.